So we just finished about molarity and molality. We talked about how the difference between them, and so molarity is defined as moles of solute divided by liters of solution. And we also talked about how molality is moles of solute divided by kilograms of solvent. One big difference is, well, the main thing is the denominator. Notice here for molarity, there's two big differences. One, it says liters. The other says kilograms. So one is in volume, the other one's by mass. There's another big difference. The molarity is liters of solution, which is solute plus a solvent. Molality is only for just the solvent. So a solution is solute plus solvent. The solvent is just, well, solvent is just the solvent. Okay, it doesn't include the solute in it, unlike that, which is solute plus solvent. Okay, so we're going to do an example of a conversion. And so here's the sample problem. What is the molality of a 5.86 molar solution of ethanol? Ethanol is an alcohol. And spam phone call. What's the molality of a 5.86 molar solution whose density is 0.927 grams per milliliter? We actually need to know the density. Why? Because one is in liters, the other one unit is in kilograms. So we need to know how to convert between grams and liters. Oh, well, here's the units. So one is in kilograms, another one is in liters. So we have a molarity, 5.86 molar ethanol. I want to know its molality. So first thing is, well, how much of this stuff do we have? A lot of these we just assume, okay? For density, it doesn't matter if you have a lot, little, density doesn't change. Well, molarity doesn't change as well if you have a lot, little. So let's just, for the sake of this problem, assume you have 1 liter of this solution, okay? You have 1 liter, or 1,000 milliliters away, you have 1 liter of a 5.86 molar ethanol solution. If you have 1 liter of this solution, then you must have 5.86 moles of ethanol. Okay, why? Because there's 5.86 moles of ethanol per liter of solution. That's the definition of molarity. Moles of solute divided by liters of solution. So if I have 1 liter solution, you have 5.86 moles of ethanol. I convert to grams. How do you do this? I know the math isn't here. Change moles to grams by multiplying by the molar mass. Molar mass is 2 carbons, 6 hydrogens, and 1 oxygen. Add that up. Carbon 2 times 12.01, 6 times hydrogen. Hydrogen is 1.01, oxygen is 16, and I can't add that quickly in my head. Whatever that adds up to, times 5.86 is equal to 270. Okay, that is the moles, or that's the grams of ethanol and moles of ethanol. Why did I change the grams? We'll come. I'll show you in a second. Okay. So, well, actually, no, I'll tell you now. That's because I want to know the mass of my solvent. Okay, I need to know moles of solute. Well, I know my moles of solute, 5.86 moles of solute. But I also need to know the mass of the solvent. I need to know the weight of the solvent. What is this? This is alcohol mixed in water. Okay, and I have 927 grams of solution. Hold on, I'm going to pause a second. Okay, so we have 927 grams of solution. How do I know that? If you have 1,000, okay, 1 liter is 1,000 milliliters. If you have 1,000 milliliters of solution and the density is 0.927 grams per milliliter of solution, you have 927 grams of solution. If you want to do the math, density is equal to mass over volume. The density, 0.927, is equal to the mass divided by 1,000 milliliters. You could solve for the mass of the solution, 927 grams of solution. Okay, or, well, it's actually right here. 1,000 milliliters times the density, 0.927 grams per milliliter, is 927 grams of solution. Why do I need to know this? This solution is a mixture of solute and solvent. A solution is like my salt dissolved in water. My salt is my solute. My water is my solvent. What I have is ethanol, alcohol, mixed in water. The weight of the alcohol and the water together weighs 927. But I actually know the weight of the ethanol, which is alcohol, is 270 grams. So what would be just the weight of the water, my solvent? It would be the weight of the solution, 927, minus the weight of my solutes, the alcohol, 270. It would be 927 minus 270, or 657 grams of water, or 0.657 kilograms of water. Again, why do I do this? This solution is a mixture of solute and solvent. This solution weighs 927. If I subtract the weight of the solute, I will have the weight of just the solvent. If I have sugar, if I have 2 grams of sugar mixed with 3 grams of water, of course 2 plus 3 is 5. The solution together would weigh 5 grams. But if I knew the solution weighed 5 grams, but 2 of them was sugar, then it would be 5 minus 2, which would be 3 grams of water. It's the same thing here. So if the entire thing weighs 927, but 270 of them is the alcohol, what's the rest? 657. That'll be the weight of just the water. So my mass of my solvent is 0.657. Now I can plug that in. The mass of my solvent in kilograms, 0.657. The moles of my solute, 8.56. Plug that in a calculator, 8.92 moles. So a 5.86 molar solution of ethanol is 8.92 moles of solution. It's molality, 8.92 moles. So these two numbers are not necessarily the same thing, okay? Lots of people say, oh, molarity and molality, same thing. No, they're not necessarily the same thing. It's like saying Celsius and Fahrenheit are not the same thing. Is there a point in which they are? Yeah, sure. But in general, they're not the same thing. Okay, so that's the example of how do we convert between, at least in this case, a molarity and molality. We'll do other conversions later. Okay, but going on with the notes. Okay, temperature and solubility. In general, solubility increases with increasing temperature. That means as you increase, like you put salt, this bottom one in yellow, if you can see that, is sodium chloride. As I increase the temperature of water, you can dissolve more and more and more salt. Okay, solubility is how much can you dissolve. Okay, in this case, grams of solute per 100 grams of water. So if I had 100 grams of water at 20 degrees Celsius, it will dissolve, I can't read this graph, like 40-something grams of salt, sodium chloride. But if I increase the temperature of boiling water, 100 degrees Celsius, I can dissolve more. It's not that much more according to this graph, but it dissolves more. Notice for potassium nitrate, much bigger difference. At 20 degrees Celsius, you dissolve under 50 grams of potassium nitrate at 20 degrees Celsius water. Well, with boiling water, you can dissolve more than 200 grams of potassium nitrate, and it'll dissolve. So most things, solubility increases at increasing temperature. However, I said that's most things. There are some substances where solubility decreases with increasing temperature. Like as you can see on this graph, sodium sulfate and cesium sulfate. And, well, that's not cesium, but sodium sulfate is one of them. Okay, so these are not common, but it happens, okay? In general, though, if you had to kind of almost like take a bet, will you dissolve more or less as you increase temperature? More things will increase solubility as you increase temperature, but that's not the case for all substances. There are some substances that decrease solubility increasing temperature. Okay, we can also use this for something called fractional distal crystallization. It's a separation of a mixture of substances into pure components on the basis of differing solubilities. So say, for instance, you had 90 grams of potassium nitrate contaminated with 10 grams of sodium chloride. Okay, yeah, 90 grams of potassium nitrate, this substance, is contaminated with 10 grams of salt. They're all mixed in. And I said, hey, separate them. And you're like, I don't know how you can separate it. It's all mixed up. They're both salts. It's like if I mix sugar and salt together, okay, and like separate the sugar and the salt. It's all mixed up. You can't. You're like, well, I'll take tweezers and a microscope or magnifying glass. Okay, good luck with that. Okay, but this is potassium nitrate, sodium chloride, all mixed up, all ground up, all together. It's contaminated. How can we separate them? We can use the fact that they have different solubilities. Notice that the solubility of potassium nitrate is very high with hot water, okay, and very low with cold water. Sodium chloride pretty much stays the same. So what I can do is I can take 100 milliliters of water at 60 degrees Celsius, okay, right there. And you can see that, well, it will dissolve. Why? Because 38 grams, if I had 100 milliliters of water at 60 degrees Celsius, 38 grams of salt will dissolve in it. I have less than 38 grams of salt. And 112 grams of salt will dissolve, potassium nitrate will dissolve at 60 degrees Celsius water. Then cool it down to 0 degrees Celsius. At 0 degrees Celsius, the salt will still stay dissolved. All the salt will stay dissolved in solution because 34.2 grams of it will stay dissolved. And you only had 10 grams of salt. But of my 90 grams of potassium nitrate, only 12 grams of salt, potassium nitrate will stay dissolved. But I had 90 grams in it. 90 minus 12 is 78. 78 grams of potassium nitrate will precipitate out or will crystallize out of this because it can't dissolve anymore. It will eventually form into pure crystals of potassium nitrate. So that's how one way we can separate out some potassium nitrate from sodium chloride. Sodium chloride will stay dissolved, but potassium nitrate, not that much can dissolve in it at low temperature water or 0 degrees Celsius water, and we can separate this stuff out. Okay, so about gases dissolved in water. You know gases dissolve in, well, I'm just assuming water right now, but this could be dissolved in alcohol, oil, whatever. If you ever had soda, you know gases can dissolve in water. Okay, solubility of gases in liquids is usually opposite of solids. That is, as we increase temperature, solubility of gas usually decreases. Okay, so as you increase the temperature, soluble gas usually decreases. Again, this is usually, there are some substances like solids that kind of do the opposite, but we're talking about in general. So solubility of a gas decreases with increasing temperature, which is also why if you had a soda and you want it to stay bubbly, okay, keep it cold. If you have warm soda, the solubility decreases with increasing temperature. And as you increase the temperature, it's going to go flatter faster because solubility will decrease. And who in the world wants to drink a warm, flat soda? Well, maybe some people do, but I don't. Okay, solubility decreases with increasing temperature. So as you increase the temperature, less and less gas will dissolve in it. Colder water will have more gases dissolved in it, which is also why it's an environmental rule that it's illegal to cut within X distance from lakes and rivers, or lakes, not just lakes, streams and rivers. And that's because the trees provide shade for the streams and rivers, and the shade keeps the rivers and streams cool. Why would it matter? It's like, well, you know, wouldn't the well, wouldn't the fish in the stream or river, wouldn't they like a little bit of sunshine and get a tan or something like that? No. Uh, for in streams and rivers, it's important that the water stays relatively cool, because if you removed all the trees against a stream or river, and this is, assuming naturally there's trees against the stream or river, it keeps it cool, the shade, because if the temperature increased a lot because of the sunshine, you will dissolve a lot. The solubility of oxygen dissolved in that water will decrease. And there can be areas where fish wouldn't be able to survive because there's not enough oxygen, because the water is just way too warm. There's not enough oxygen dissolved in the water. So that's why it's illegal to cut trees within a certain distance. I'm talking about more for logging companies, maybe not a single individual tree on private property, but I'm talking about for major, like again, like logging. Solubility decreases because solubility decreases increasing temperature. If we cut away all the trees against the sides of a river, the water in the river will increase such that whatever animals that are in the river may suffer from it. Okay, the solubility of gas in a liquid is proportional to the pressure gas over a solution. It's also known as Henry's law. Let's not worry about the equation right now, but basically what it says is the concentration in molarity of gas dissolved is equal to some sort of constant, K, times the pressure. In other words, the more pressure there is above a gas, the more gas will dissolve in it. The lower pressure above it, the less gas will dissolve in it. Low pressure, not a lot of gas dissolved in it. High pressure, a lot of gas dissolved in it. Example of that would be, I don't own one of these devices, but the soda stream is something that where you can make soda or bubbly water at home. How it works is you have this little bottle or a special bottle, and you put regular water in it. And you hook up the water bottle. It's just regular, it could be like tap water or filtered water. So you put water in it, and you put it into you seal it into this into the machine. And then the machine is like a straw that goes into the water. You push some button. Again, I've never used one of these because I don't own one. You push some button, and high pressure carbon dioxide bubbles into the water. And high pressure carbon dioxide means high amounts of carbon dioxide will dissolve in it. Low pressure, not a lot will dissolve in it. So if you like fizzy water, you would push the button, I don't know, probably once. If you want it extra fizzy, maybe you push it twice. And another thing that's important, remember, low temperature. Low temperature. You want more water or gas to dissolve in your soda, make it cold water, okay? You want cold water in it. If you have warm water, you'll have less gas dissolved in it. If you put boiling water, I don't know why you would do that, you will not have a lot of gas dissolved in it. So the amount of gas dissolved in water depends on temperature plus the pressure of the gas above that liquid. Okay, so we'll just pause for here.